Welcome to my wonderful world of tuples. Tuples and polynomials. If you're not at all familiar with tuples, I would strongly recommend Tuples 101 Basics, and you get there with YouTube /user/RJAINCHELL. I think we will find that using tuples to represent polynomials will make the operations with polynomials much simpler. Here we have a polynomial, 3x squared plus 5x plus 9 is written in correct order. It's x squared, then the next term to the right is x, and the next term has no x. So we can simply take off the numbers 3, 5, and 9 and make the tuple 3, 5, 9. 3x squared minus 9, the next example, has no x term, but we have to understand that it's really 0x. So when we write the tuple, we've got 3, 0, negative 9. Look at our third example. We've got 4 plus 17x squared minus 9x plus x cubed. Things are out of order. We need the leftmost power of x to be the x cubed. Then we want an x squared, then an x, and then a number. So I've rearranged the terms, and now x cubed by itself is one of them. So we got 1, comma, we got 17x squared, so the 17 comes down into the tuple. Minus 9x, the minus 9 comes down, and the 4 comes down to make the end of the tuple. So the tuple is 117 negative 9, comma 4 is the tuple that represents the polynomial. Here we have a tuple representing a polynomial. So we have to start with the 3 on the right hand side and count in successive order x, x squared, x cubed, and so forth. So we would have 3, then an x, then an x squared, the x cubed, x to the fourth, x to the fifth. So we have 2x to the fifth. And then the negative 1 was with the x squared, so minus x squared and plus 3. And the next one we got, starting from the right, number, x, x squared, x cubed, x to the fourth. So minus 1x to the fourth, but don't put the 1, minus x to the fourth, plus 2x cubed. There's no x squared term. Leave it out, and we have 2x, and then minus 1. Well, we have two tuple polynomials that we don't want to add. It would be simpler to put them in a box array, and that's what we see below. So when we just put the integers in the boxes, we've got 9, and negative 6 is 3, 12 and 8 is 20, negative 4 and 0 is negative 4, 0 and 11 is 11, 0 and negative 14 is negative 14, and the 5 we bring all the way down. We've added the two polynomials. What is this polynomial at the end? Start with the 3. So it's number x, x squared, x cubed, x to the fourth, x to the fifth. So at the bottom we see 5x to the fifth minus 14x to the fourth plus 11x cubed minus 4x squared plus 20x plus 3. We could just remove all the x's from the problem and just work in the vertical and horizontal lines and just keep our answers as 5, negative 14, 11, negative 4, 20, and 3, and the original polynomials as tuples. Here we have the subtraction of polynomials. We will change every subtraction into an addition problem. Notice, take the negative of every number in the second row. The negative of a negative is a positive. So now we have 14. The negative of 11 is negative 11. 0 is 0. The negative of 8 is negative 8. And the negative of negative 6 is 6. Okay, now the negative sign becomes a positive sign, and we simply add. So we have 9 and 6 is 15. 12 and negative 8 is 4, negative 4. And 0 is negative 4. 0 and negative 11 is negative 11. 0 and 14 is 14, and we have a 5. It's much easier to change everything into an addition problem. Multiplication of polynomials. We have 4 and negative 3 stands for 4x minus 3. And we have just the number 11. We simply do 11 times negative 3 is negative 33, and 11 times 4 is 44, and our new polynomial is 44x minus 33, but we'll just keep it as tuples. Now we have the multiplication minus 9, comma 7, standing for negative 9, x plus 7 and 3 negative 5, which stands for 3x minus 5, and we'll multiply them. It's very simple. Negative 5 times the 7 and the negative 9. So negative 5 times 7, negative 35. Negative 5 times the negative 9 is a positive 45. Now we do the 3 times the 7 and 3 times negative 9, but the 3 is really 3x. We have to put a 0 under the negative 35, and then we do 3 times 7 is 21. 3 times negative 9, that's negative 27. And we're going to add these numbers. So negative 35 and 0 is negative 35. 45 and 21 is 66. And the negative 27 simply comes down. So our final tuple is negative 27, 66, negative 35. Now we have 11, negative 5, 23, negative 15, 17. That's going to be multiplied by 4, comma, negative 8, comma, 9. We'll do them mentally. 9 times 17. 9 tens is 90. 9 sevens is 63. That's 153. Okay, 9 times 15. 9 tens is 90, and 9 fives is 45. That's 135, but negative. Okay, 9 times 23. 9 20s, that'd be 180, and 9 threes is 27. That makes 207, and 9 times negative 5, negative 45. 9 times 11 is 99. Okay, now we do negative 8 times each one of the top row numbers. So negative 8 times 17. We got 8 tens is 80, and 8 sevens is 56. That'd be 136, but negative. 8 and negative 8 times negative 15, positive. 8 tens is 80, and 8 fives is 40. That'd be 120. Negative 8 times 23, negative. Okay, 8 20s is 160, and 8 threes is 24. That's 184. And you got negative 8 times negative 5, that's positive 40. And negative 8 times 11, negative 88. Now we do 4 times the numbers on the top. So 4 times 17. Okay, 4 tens is 40, 4 sevens is 28, that's 68. 4 times 15 is 60, so we got negative 60. 4 times 20, 4 times 20 is 80, and 4 threes is 12, that'd be 92. 4 times negative 5, negative 20, and 4 times 11 is 44, and then we add them. So if 153 and a bunch of zeros, that's 153, and you add negative 135, 130 is 6. That'd be negative 271, and similarly we get 395, negative 289, 231, negative 108, and 44. And we say, okay, what's the 44x to what power? Well, we count from the right to the left. We got number x, x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. And that makes sense because originally the 11 is x to the 11x to the fourth, and the 4 is 4x squared. So it's much easier doing this with tuples than putting all the x's in, lining up the numbers, the x's, the x squares, the x cubes, the x to the fourth, x to the fifth, and x to the sixth. Division of polynomials. Now, the polynomials are written in tuple form. We're dividing by 1 comma negative 3. That stands for x minus 3. That's going into the dividend 1, 7, negative 2. That stands for x squared plus 7x minus 2. It goes in 1 comma 10 times. That's x plus 10, and the remainder is 28. And then we'll go over to the mechanics on how we get there. The key number in the divisor that we must focus on is the 1 in the 1 comma negative 3. When we ask ourselves, how many 1s make up 1 in the 172? 1. 1 times 1 is 1. Okay, so you do 1 times 1 and 1 times negative 3. That's over on the right. It was 1 comma negative 3. And we're going to subtract that. Now, for subtraction, we're actually going to put the subtraction to each of the numbers 1 and negative 3, and that becomes negative 1 plus 3, and then we get to add the numbers. So 1 comma 7 added to negative 1 plus 3. The 1's go away, which is what we want, and 7 and 3 is 10. Now we ask ourselves the question, what times 1 gives you 10? 10. 10 times 1, 10 times negative 3. As we look on the right, it was 10 and negative 30, and we will subtract this, but we will apply the negative inside the tuple, so we have negative 10, and a negative of negative 30 is a plus 30. So when we add them, the 10 and the negative 10 go away, and negative 2 and 30 gives 28 for the remainder. Now, a 2 tuple goes into a 2 tuple. That's why the first one in the quotient was above the 7. Now we have different ways of writing division. In the problem we just did, the divisor, that's d of x, is going into the polynomial p of x. It goes in q of x times, that's the quotient, and we're left with a remainder. If we write this as an equation, the original polynomial p of x divided by d of x goes in q of x times plus the remainder of x. So we have p of x is equal to d of x times q of x plus r of x. For the previous division example that we just had as tuples, 1, 7, negative 2, that was the dividend. It's equal to the divisor, 1, negative 3, times the quotient, 1, 10, plus the remainder. As polynomials, x squared plus 7x minus 2. The dividend is equal to the divisor, x minus 3, times the quotient, x plus 10, plus the remainder, 28. We will use the p of x is equal to d of x times q of x plus r of x later. Here we have a division. We're going to divide x squared plus 4x minus 5 into x to the 4 plus 7x cubed minus 2x squared plus 7x minus 2. But we've shown it as tuples. Now, 1, 4, negative 5 is a 3 tuple. 3 tuples go into 3 tuples. So the first number in the quotient will be above the negative 2. And we ask ourselves the question, how many 1s in the 1, 4, negative 5 give you the 1 in the dividend? 1. So we do 1 times 1, 4, negative 5. We get 1, 4, negative 5. We're going to subtract. So I'm going to apply the negative to each number and add it to the top 3 numbers. So 1 and negative 1, that's 0. We don't write it down. That's what we wanted. We have 7 and a negative 4, that's 3. And then we have negative 2 and a negative of a negative 5, which is 5. So we have 3. We bring down the 7. We ask ourselves the question, what times 1 gives us 3? 3. 3 is our next digit in the quotient. Okay, 3 times 1, 4, negative 5. We would get 3, 12, negative 15. We will subtract. So I'm going to apply the negative and add. So we have 3 minus 3, that's 0. That's what we wanted. And then we have 3 and a negative 12, that's negative 9. We're going to have the negative 15, that's 15, and 7, and that's 22. We bring down the negative 2. And we ask ourselves the question, what times 1 gives us negative 9? Negative 9. So that's the last digit in the quotient. And negative 9 times 1, 4, negative 5 is going to give us negative 9, negative 36, and a plus 45. We will subtract. We will apply the negative and add. So the negative 9 is a positive 9, and negative 9, that's 0. That's what we wanted. The negative of negative 36 is 36, and 22 is 58. And then we have negative 2 and a negative 45, that's negative 47. Our remainder is 58, negative 47. It's actually 58x minus 47. And the quotient is x squared plus 3x minus 9. If you were to multiply 1, 4, negative 5 times the 1, 3, negative 9, and add to it the remainder, 58, negative 47, you will get the dividend. Now we're dividing the tuple 1, 2, 3 into 2, 5, 7, negative 1, 3, 8. 3 tuples go into 3 tuples. So we're going to start above the 7 in the 2, 5, 7, negative 1, 3, 8. We ask ourselves, how many 1s give you 2? 2. Okay, 2 times 1, 2, 3 is 2, 4, 6. Now, we're going to subtract each of those numbers, negative 2, negative 4, negative 6, and add them to the 2, 5, 7. So 2 plus a negative 2, that's 0. That's what we want. We slide over. And then a negative 4 added to 5 is 1, and a negative 6 added to 7 is 1. We bring down the negative 1. Then we ask, what times 1 gives you 1? 1. So 1 times 1, 2, 3 is 1, 2, 3. We apply the negative to each number and then add. So we get 1 and a negative 1. That's 0. That's what we wanted. We slide over. And a negative 2 added to 1 is a negative 1. And a negative 3 added to a negative 1 is negative 4. We bring down the 3. And then we ask, what times 1 gives you negative 1? Negative 1. Negative 1 times 1, 2, 3. That's negative 1, negative 2, negative 3. But now we apply the negative and add. So we'll have negative 1 is 1 plus a negative 1. That's 0. That's what we wanted. We slide over. A negative of a negative 2 is a 2 plus a negative 4 is a negative 2. And a negative of a negative 3 is a 3. Plus a 3 is 6, and we bring down the 8. Then we ask the question, what times 1 gives you negative 2? Negative 2. Okay, that's up in the quotient. Now, negative 2 times 1, 2, 3 is negative 2, negative 4, negative 6. We apply the negative and add. So we'll have 2 plus a negative 2, that's 0. That's what we wanted. And negative of negative 4 is 4 plus 6 is 10. And the negative 6 is 6 plus 8 is 14. So our remainder is 10, 14. That stands for 10x plus 14. And at the top, the quotient, you start from the right. Number x, x squared, x cubed. So it's 2x cubed plus x squared minus x minus 2. This is the same as the previous division. And I'm not going through all the details, but we're going to divide 1, 2, 3 into 2, 5, 7. That goes 2 times. And 2 times 1, 2, 3, that's the 2, 4, 6. And instead of bringing the negative 1 down, we notice that negative 1, 3, 8 is a 3 tuple. And you can go 1, 2, 3 into negative 1, 3, 8 goes negative 1 times. Negative 1 times 1, 2, 3, that's negative 1, negative 2, negative 3. And you subtract, and you would then get a 0. And 3 and a negative 2 is positive 2, that's 5. And a negative 3 is a 3, and 8 is 11. And you're on your way to getting to the final remainder of 1014. But this is a demonstration that my new method for division, which is in Tuples 101 Basics, also applies to polynomials. We will now consider plugging in values for x and finding the value of a polynomial at those values. So we'll start off with a simple polynomial, 6x squared minus 4x plus 5. Now, P of 5, wherever you see x, you put 5, and we'll have 6 times 5 squared minus 4 times 5 plus 5. Add all those numbers up and you get 135, and that's a typical way of determining polynomial values if the polynomials are relatively simple. Now, consider a times b is equal to 10. Then if we divide both sides by b, a is equal to 10 over b. And we're going to let p of a equal m. Figure out m. Now, p of a is equal to 6 times a, 10 over b, squared minus 4, 10 over b, plus 5, that's equal to m. And if you multiply both sides by b squared, you would then have 6 minus 4b times 5b squared is going to be equal to mb squared. Divide both sides by b squared, and now p of a will equal 6 minus 4b, 5b squared. That's a tuple divided by b squared. Now, for our case, we had a is equal to 5, and so b is equal to 2. And then we will calculate p of a by plugging in 2 for b. And if you plug in the 2 for 6 minus 4b, 5b squared over b squared, and you plug in 2, you get 540, and then you divide it by b squared 4, you will get 135. Here we have the polynomial p of x, and it's equal to 2x to the 5th minus 3x to the 4th plus 7x squared minus 4x plus 1. And the next few slides, what we're going to try to do is determine p of 3 1/3 by different methods. the most direct way is to simply, wherever you see x, you put 3 1/3. So we got 2 times the 3 1/3 to the 5th and so forth. It's not too bad. If we change the 3 1/3 to an improper fraction, it'd be 3 times 3, that's 9 plus 1, so we got 10 over 3. Now, 10 over 3 to the 5th, to the 4th, and so forth is relatively easy. By the way, you might notice there is no 10 to the over 3 to the 3rd power because there is no x to the 3rd, so we don't have to worry about that. But when we perform the calculation, 10 to a power is easy, and 3 to the 5th, to the 4th, and so forth, that's easy. And the common denominator will be 243, that's 3 to the 5th. So it's not that hard to calculate p of 3 1/3. And at the bottom we see the final answer is the mixed number, 518 and 29 over 243. Our second method for determining p of 3 1/3 is to use the remainder theorem. We will now divide x minus 3 1/3 into the polynomial. You might notice we have the 2, -3, 0. That was for the x cubed term, 7, -4, and 1. And we don't do 1, 3 1/3. You can think of this as x minus 3 1/3. What do you put into x to get 0? 3 1/3. So it's a negative sign instead of just 3 1/3. Now, we do, what times 1 is 2, 2, 2 times 1, 2, 2 times negative 3 1/3 is negative 6 2/3, subtract, and so forth. And you grind it down, and you will get 518 and 29 over 243. Quite a few steps, but that's how you do the remainder theorem. In this approach, we're still using the remainder theorem, but the way the division was performed, we divide 1 comma -3 1/3 into 2 -3, and we divide 1 comma -3 1/3 into 0, 7, and we then go to the 1 comma -3 1/3 into -4, 1. That's the new division method, and we'll form a tuple and have different colors. And so above the division line we have quotient digits 2, 0, -4 on the first row. The upper next row is 3 2/3 and a 7 and so forth. And we grind it all the way down again. It's still 518 and 29 over 243. So it's a different approach on doing division, but it's still the remainder theorem and we get the same answer, but it's still quite a few steps. We will now consider a new method for determining p of x. And again, we'll use x is equal to 3 1/3 and figure out the value. Take a new approach. Now, we'll do a times b is 10. We divide both sides by b. A is equal to 10 over b, and what we're interested in is finding p of a, but instead of using a, we will use 10 over b. So we plug it in. You got 2 times 10 over b to the 5th minus 3, 10 to the 4th over b. We don't have a 3 power because there is no x cubed and so forth. And then if you multiply both sides by b to the 5th, you'll get 2 times, and we look at it, 10 to the 5th. Next term is a 10 to the 4th, then a 10 squared, a 10, and no 10. And you might notice that 10 to the 5th, and then 4 plus 1 in the next term adds up to 5. 2 and the 3 add up to 5, and the 1 and the 4 add up to 5, and we have a 5 as exponents. Easy way of keeping track of it. And then we take a notice that the term 2 times 10 to the 5th minus the next term 3, 10 to the 4th times b to the 1st plus 7 times 10 squared times b cubed minus 4 times 10 times b to the 4th plus 10 to the 0, which is 1, times b to the 5th. That can be written as the tuple 2 -3b 0 b squared 7b cubed minus 4b to the 4th and b to the 5th, and we got to divide by b to the 5th. if we let A equal 3 1/3, divide 3 1/3 into 10, you will get B is equal to 3. So now when we calculate P of A, we're going to plug it in to the formula of P of A with the B's. And when you plug in B equals 3, you'll get 2, -9, 189, and so forth. Got 125,903 divided by 243, and you will get 518 and 29 over 243. We will now have some more examples with this new approach. Now we consider a polynomial that the highest exponent on x is 8. And we use our formula. We're going to find P of 5, and 5 times 2 is 10. And we'll be plugging 2 into a formula. And we see P of 5, it's 7. Then comma, 9 times 2 to the first. And then our next term will have 2 squared. And the next term will have 2 cubed. And we put the coefficients of the polynomial down. That's 7, 9, -2, -3, 12, 23, 11, and 1, -1. But we also have a 0 because there's no x to the 6, and that's at 0 times 2 squared. And we're going to form a tuple, and that tuple will be divided by 2 to the 8th. And we have those numbers down below. We got 7 and comma, and then 9 times 2 is 18. We got the 0. And then you got minus 2 times 2 cubed. That's minus 16. And we keep going, and we divide by 2 to the 8th, which is 256. We form the tuple, and that's 8, 7, 8, 4, 6, 5, 0, 2, 4. And that's very easy to do. You would add 300 to the 256. Then you subtract 30 and so forth, and we convert the tuple to single digits. And since the last digit to the left is 8, it's a single digit, we have the number 878465024 divided by 256, and that comes out to be 3,431,504. Now, we'll consider the same polynomial we did before when we found P of 5. Now, let's say we want to find P of 2 by the same method. So, if A is 2, then B is 5. And then when you plug the numbers in, you have 7 times 9 times 5 to the first, 0 times 5 squared, minus 2 times 5 cubed, and we go all the way up to -1 times 5 to the 8th, and you divide by 5 to the 8th. And then you work out those powers of 5, and you'll finally get to the tuple 11,878,90625, and you divide that by 5 to the 8th, which is 390625, and you get 3,041. Now, it would have been much easier to just go ahead and plug the 2 in. So although you have another method to figure out P of 2, doesn't mean that you should always use the tuple approach, because it would have been much easier just to plug 2 into 7 times 2 to the 8 plus 9, 2 to the 7, and so forth. Here we have the polynomial again. P of x is 7x to the 8 plus 9x to the 7 minus 2x to the 5th, and so forth. And we're going to find P of -3 1/3. So we have to ask ourselves, what do you multiply by -3 1/3 to get 10? That would be -3. So to find P of -3 1/3, we see in the tuple below we have 7 times 9 times -3 to the first, 0 times -3 squared, then we have -2 times -3 cubed, then -3 times -3 to the fourth, then 12 times -3 to the 5th, then 23 times -3 to the 6th, then 11 times -3 to the 7th, and then -1 times -3 to the 8th, and we're going to divide by -3 to the 8th. We'll work out all those numbers that's shown below. The 7 on the leftmost number of the tuple indicates that the tuple will probably be positive. When you convert that tuple into single digits that are either positive or 0 integers, we have 431483,569 divided by 6561, which is -3 to the 8th. And you do the division, you get 65,764, and the fraction 5,965 over 6,561. Below I have shown how to convert the tuple into an integer. And you could also see this under the video Tuples and also the Tuples 101 Basics. Now, minus 6,561 on the right. You have to add multiples of 10 or subtract multiples of 10. If you add 6,570 to minus 6,561, you get a 9. By adding 6,570, you must subtract 657. And you add the negative 657 to the negative 24,057, and you get negative 24,714. We start over. What do you add to that to get a positive integer? That would be that single digit. That would be 24,720. You get a 6. Since we added 24,720, we must then add in the next column negative 2,472. We add them, we get 14,295. And you ask yourself, how do we get that to be a single digit positive integer or 0? You would subtract 14,290. That would give you 5. Since you subtracted negative 14,290, you must now add in the next column for 1,429. And then you continue all the way out to the end. Here we have the polynomial. P of x is equal to x cubed, which is 1x cubed, plus 2x squared, plus 3x, plus 4. And we want to determine P of a. If we write it in x's, it's x minus a is going into the polynomial x cubed plus 2x squared plus 3x plus 4. If we do it as tuples, x is represented by a 1, comma, minus a. We're finding the value at a, so it's got to be 1, comma, negative a. You can think of this as what makes x minus a 0. What value for x? A. Okay, now we're going into 1, comma, 2, comma, 3, comma, 4. You ask yourself the question, what times the 1 in 1, comma, negative a equals the 1 in the 1, 2, 3, 4? 1. So 1 times 1, comma, negative a is, as you see below, 1, comma, negative a, and the operation is subtract. So the 1's will go away, and a negative a is a, and then 2 plus a is there below it, and then you bring down the 3. You ask yourself the question, what times the 1 in the 1, comma, negative a equals 2 plus a? 2 plus a. And then you do that, and you keep going, a lot of steps, and you will find the bottom tuple, one tuple, is 4, comma, 3a plus 2a squared plus a cubed, and that is in number, so I've written it so the highest exponent is on the left. We have a cubed plus 2a squared plus 3a plus 4. And you might think about this. We could have gotten that same value just simply plugging in a for x in the polynomial and not have gone through all the steps. So this brings the point, why do we use the remainder theorem? Well, the key is if P of a equals 0, that means that x minus a divides x cubed plus 2x squared plus 3x plus 4 with 0 remainder, and the quotient is the other factor times x minus a that gives you the polynomial. Now that is an approach with the remainder theorem. However, what I'm going to show you next is that we don't want to take all those steps. So we've got 3 ways of determining P of a. We can do the remainder theorem, simply plug it in, and we see by all the little steps we do, that's essentially what we're doing with the remainder theorem, and we can do it by the tuple approach. Here we have the polynomial q, a number times x cubed plus r, a number times x squared plus a number times x plus another number t. So instead of 1, 2, 3, 4, we got q, r, s, and t. We do the exact same division process with the remainder theorem, and we will find that the quotient is q, comma, r plus qa, comma, s plus ra plus qa squared. Now that is a quadratic. So the q is qx squared plus r plus qa times x, and the s plus ra plus qa squared is the number. Now, if P of a equals 0, then that means that the quotient times the divisor equals the polynomial. So we don't have to keep doing all the steps. We have a form to just plug in numbers to find the quotient when P of A is 0. And we could do this for any degree polynomial. But so if we were doing cubics, we would never have to go through all these steps again. So you could do it for quadratic, that's x squared, x to the 4th polynomials, x to the 5th polynomials, doesn't matter what it is, you could work out all these steps ahead of time. And so whenever P of A is 0, you would already have the factor. You wouldn't actually have to go through the steps of the remainder theorem, which takes too much time, when you can form the form and you have it immediately, and you only use that form when P of A is equal to 0. Here we have a general polynomial. P of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so forth, all the way down to a sub 1 times x to the first plus a sub 0. And what we want to do for certain values of a is find P of A, and we have three methods. You plug in a and do it directly, or you can form a tuple and determine P of A, or you could use the remainder theorem. So these two cases, where we plug the a in directly or we use the tuple form, will be discussed for various cases. Our first case is a strange one. A is equal to 1, then b is equal to 10, because 1 times 10 is 10. And the question is, would you want to use the tuple approach, or could you just plug in 1? And I think we would want to just plug in 1, and that's shown on the next slide. But if a is 2.5, 4 times 2.5 is 10, you may well want to use the tuple form. The same for if a is 1 2/3, 6 times 1 2/3 is 10, you might want to use the tuple form because b is 6. Then we have a case, a is 13. What times 13 is 10? Well, 10 over 13. You might want to just go ahead and use a is equal to 13 and do it directly. And then if we have another type case, a is equal to 20, b is a half, but you can then use, say, a is 30, use a third, a is 40, use a fourth, and so forth. And we'll take a look at both of them and see which way is easier, just plug it in directly or to use the tuple form. Here we have the case, a is 1 and b is 10. Now, P of 1 is a sub n times 1 to the n plus a sub n minus 1 times 1 to the n minus 1, all the way down to a sub 1 times 1 to the 1 plus a sub 0. 1 to any power is 1, so it becomes just the sum of the coefficients, a sub n plus a sub n minus 1, all the way down to a sub 0. If we try the tuple approach, P of A would be equal to the form as we see it. You get a sub n, comma, a sub n minus 1 times 10, then a sub n minus 2, 10 squared, which is 100, all the way down. And what we're going to do, starting on the right, we'll make everything 0 except for the leftmost cell. So you would subtract a sub 0 times 10 to the n, then you must add in the next cell a sub 0 times 10 to the n minus 1. And that would create a 0 in the rightmost cell. You keep continuing this on, and at the end you would have all the sum, the coefficients as a sum in the leftmost cell, and then it would be followed by n zeros in n cells. And if you form the integer, you can divide by 10 to the n, and 10 to the n has n zeros. All the zeros cancel out, and we're left with the sum of the coefficients. That's a lot of work, so we would not use the tuple approach in order to figure out P of 1. We now have the case a is 2.5. 4 times 2.5 is 10. We'll take the polynomial 4x cubed minus 5x squared plus 3x minus 2, and P of 2.5, if you were to do it directly, it's equal to 4 times 2.5 cubed minus 5 times 2.5 plus 3 times 2.5 minus 2. We will now show it with the tuple approach. P of 2.5 is equal to 4, that's from the 4 times x cubed, minus 5 times the 4 times the 2.5, that's where that 4 comes, comma, 3 times 4 squared, then minus 2 times 4 cubed, so the exponents went 1, 2, 3, and you're dividing by 4 cubed. Okay, we formed the tuple, 4, negative 20, 48, negative 128, so we would convert that to an integer. You would add 130, take away 13, and so forth, and you would get 2,352 divided by 64, and that turns out to be 36 3/4. Now that we have the case a is 1 2/3, 6 times 1 2/3 equals 10. Take the same polynomial we used on 2 1/2. So we've got 4 times 1 2/3 cubed minus 5 times 1 2/3 squared plus 3 times 1 2/3 minus 2. We'll use the tuple approach. So p of 1 2/3 is equal to the coefficient 4 minus 5, the next coefficient, times 6, the next coefficient 3 times 6 squared, the next coefficient negative 2 times 6 cubed, and we'll divide by 6 cubed. We will then form the tuple 4 negative 30, 108 minus 432. To start it off, you would add 440 and take away 44 in the next cell, and you work that out. It's 1,648, and you divide by 6 cubed, which is 216, and that works out to be 7 and 629 over 999. And if you want to write it as a decimal, it is equal to 7.629 repeats forever. Now we have the case a is 13. And if you multiply 13 by 10 over 13, you will get 10. It would be much easier just to plug the 13 into the polynomial and work it out, as opposed to forming the tuple. So in this particular case, p of 13 is equal to 4 times 13 cubed, that's 2197, minus 5 times 13 squared, 169, plus 3 times 13 minus 2, and that works out to 7,980. Here we have a is equal to a half. Now, 20 times a half is 10. So we have two ways we can do it. You can simply plug in a half for x and work it out directly. And then p of a half would be 4 times a half cubed, which is an eighth, minus 5 times a half squared, which is a fourth, plus 3 times a half minus 2. Get a common denominator of 8, and you could work it out. Or we could use the tuple approach, and that's what's below. P of a half is 4 minus 5 times 20 to the first, comma, 3 times 20 squared, comma, minus 2, 20 cubed. And you see in the tuple below, that's 4 minus 100. Then we have 3 times 400, that's 1200, minus 2 times 8,000, that's negative 16,000, divided by 20 cubed, which is 8,000. And if you then turn the tuple into an integer, you will find that you will have, starting from the right, 3 zeros and a 10, and that's negative 10,000 over 8,000. You knock out the 3 zeros, you got minus 10 over 8, divide by 2. On the numerator and denominator, that's minus 5 over 4, which is minus 1 1/4, which is minus 1.25. Here we have the case a is equal to 20, and then b is equal to half. Half times 20 is 10. But we won't use the tuple approach. We'll just simply plug the 20 in. So with our polynomial that we've been using, 4x cubed minus 5x squared plus 3x minus 2, we have p of 20 is 4 times 20 cubed minus 5 times 20 squared plus 3 times 20 minus 2. So 20 cubed is 8,000, so 4 times 8,000, that's 32,000, minus 5 times 400, that's minus 2,000, plus 60 minus 2, and this is relatively simple. 32,000 minus 2,000, that's 30,000, plus 60 minus 2 is 58, so we got 30,058. Here we have the case a is 2/3. Now, 30 over 2 times 2/3 is 10, and 30 over 2 is 15. So we can do this two ways. We can do p of 2/3 is 3 times 2/3 cubed plus 2 times 2/3 squared plus 1 times 2/3 plus 0. Or we could say, okay, p of 2/3 is equal to 3, comma, 2 times 15 to the first, comma, 1 times 15 squared, comma, 0 times 15 cubed. And that whole quantity, that tuple divided by 15 to the third. And so what we have is 3, comma, 30, comma, 225, comma, 0 over 3,375. We change the tuple into an integer and divide by 3375. and that's 8,250 divided by 3375. That goes in twice, and you got 4 9ths left over. And if you want to write it as a decimal, that's 2.4 is repeating. Here we have the case A is equal to 711. 110 over 7 times 711 is 10, so B is 110 over 7. We could do the problem directly, P of 711, just by plugging in 711 for X. And if we try the tuple approach, we would have 3, 2, 110 over 7, 1, 110 squared over 7 squared, and the 0 term, and then our denominator is 110 over 7 cubed. Now, if we multiply by a well-chosen 1, 7 cubed over 7 cubed, we can clear the denominators in the tuple. What we'd be left with is on the numerator, we'd have 3 times 7 cubed. Then we have 2 times 110 over 7 times 7 cubed. That would leave 7 squared in the numerator. And 1 times 110 squared over 7 squared times 7 cubed. And we'd have 7 in the numerator. And the 7 cubes would cancel in the next term, but it's 0 times it, so it's still 0. Over 110 cubed over 7 cubed times 7 cubed, and the 7 cubes cancel. So in our somewhat simplified tuple, we have the 1029, 10780, and then 84700, and a 0 divided by 1331000. When you change the tuple into an integer, you would have 2954000 divided by 1331000. The zeros cancel. And when you divide 1331 into 2954, it goes in 2 times. You got a remainder of 292 over 1331 into 3 decimal places. What we have as an answer is 2.219. Here we have the same problem from before. A is 711, B is 110 over 7. And this time we're going to plug it in directly. So P of 711 is 3 times 711 cubed plus 2 times 7 over 11 squared plus 1 times 711. We'll have a common denominator of 11 cubed, 1331. So we do 3 times 7 cubed, that's 343 over 11 cubed, that's 1331. Then you got 2 times 49 times 11 over 1331, and we'll multiply by 7 times 11 squared in the numerator and 11 squared in the denominator. So we have 7 times 121. Those numbers should be familiar. That's 1,029 plus 1,078 plus 847 over 1331. Goes in 2 times, and you got a remainder of 292 over 1331. I think that's simpler to do it directly with this particular A value, 7 over 11, than using the tuple approach. Here we have the cubic form x cubed plus a, x squared plus bx plus c, where a, b, and c are integers. And we want to know if that's factorable as x plus d, with d an integer. And if d is an integer, then e and f, and x squared plus ex plus f will also be integers. And we set up simple equations. We multiply x plus d times x squared plus ex plus f. So the coefficients of x cubed on both sides is 1 is equal to 1. Then the coefficient on the right hand side of x squared is the same as a, and that's d plus e. The same for b is d plus e plus f, and c is equal to df. Now, the possible integer values for d are the divisors of c, which is 3. So we either have plus or minus 1, plus or minus 3. We set up these simple little equations. We'll let f equal 3. Then that forces d to be 1. That implies d is equal to 2e. And then all we have to do is decide, does 5 equal to de plus f? It does indeed, so the answer is yes. Now what we've done is factored x cubed plus 3x squared plus 5x plus 3 into x plus 1 times the quadratic x squared plus 2x plus 3. Now 1 is not the 0 of the cubic. It is negative 1, because negative 1 plus 1 is 0. You could then do the division, as is normally done, to get the x squared plus 2x plus 3, but it's much simpler just to use these simple little equations. So you don't need to do synthetic division or tuple division to find these numbers. Now, x squared plus 2x plus 3, you set that equal to 0. So how you go figure that one out? What x's make that 0? You got two possible methods. It doesn't factor. So you could either complete the square, or you could use the quadratic formula, and you can find that those are not rational numbers. They are actually complex numbers. They have an I term in them. Coming attractions, tuples and number bases. And the bases to be covered will be base 2, base 5, and base 10. Some will be a repeat from my other videos, but for each base, we will learn how to change base 2 tuples into base 2 integers. The same for base 5 and base 10, and we'll learn how to, in each base, how to add, subtract, multiply, and divide.